Okay, so this is a question that's confused me personally for quite some time. It involves finding the potential everywhere given some sphere of charge with a radius. Okay, um, so they might ask you to find the electric field inside and outside the sphere, or they might give it to you. I just solved this question up to the point where you find the electric field because I want to focus on finding the potential in this video. So there's two main methods I've found of how to do this. One might make more sense to you than the other, but I'll go over them both, starting with the method of how we learn how to do this in class, and that's with using definite integrals with defined bounds. Okay, so that's going to be method one. An important thing to keep in mind is in this course, the potential VAB is not, it's not VA minus VB in this course, okay, or at least not in the textbook. It is instead equal to VB minus VA. That's how it's written. If you want to go over the textbook, that's how it's written. And written in the line integral form, it's an integral from A to B, like so. Okay, so this is something I'm going to keep going back to when I break down the more complicated part, which is finding the potential inside. So keep that in mind for now. So for the first part, we're going to consider when the radius r is greater than a, or we're outside the sphere. So when we're worrying about this case, that's when we're trying to find some point at infinity, and we want to take this point at infinity as reference and find the potential at some random r, so long as it's bigger than a. This is our sort of contract for this case. Whenever r shows up, we already assume it's bigger than a. Okay, so moving on, that would make our integral for the potential outside when r is greater than a equal to the negative integral from infinity to r, as we just talked about. And then you put the electric potential outside the sphere in here, so that would be rho a cubed over 3 epsilon naught dr. And once you solve that, you're going to end up with rho a cubed over 3 epsilon naught r. Okay, so that's really all you need to do for the first case when you're looking at potential outside the sphere. So again, this can be rewritten basically as from this relationship, from these integral bounds, you can relate it back to this formula that we know. So this is like saying this is VR minus V at infinity. Okay, and I'll get back to this again later when we look at the second case right now. So for case 2, R is less than A, or we're inside the sphere now. And drawn here, what that would look like is we need to basically split the integral into two now. We need to split our integral into two sets of bounds. One from infinity to A, and another from A to whatever R might be inside the sphere here. As long as R is less than A, because remember for this part, our contract is R is less than A whenever it shows up. So to do that, like I said, we need to bust up this integral into separate bounds. So the way they want you to do it from class is they want you to start from the outside and go in, just like how we did for this part. So let's see what that would look like. You would have the potential from infinity now to A instead of R of the outer electric field, which would be this guy just above. And now we need to add the potential integral for the bound inside the sphere. So I'm adding it, but the potential is a negative integral, so that's why there's a negative here. And you'd go from A now to R. And you'd put the electric field inside when R is less than A in here. Whoa, that's a really thick line. There are DRs in here. Okay. And now if we look at how this is written, for a long time I didn't quite understand why exactly this works out. And to be honest, I really don't understand it a whole lot more either now, but it might make you feel a little more comfortable doing this method if you take a look at these line integrals and you relate it back to our known definition here, right? So, VB minus VA is equal to the integral from A to B here. So, this must be the same as VA minus V infinite minus VR minus VA. Sorry. There should be a plus here instead, okay? Because we're adding the potentials, of course. My bad. I said that myself, and yeah. Anyway, sorry. So this is what's happening with these integrals here. You have the potential at A with reference to potential infinity, and you're adding the potential at some r less than A with reference to, the potential at r at some r less than A with reference to the potential at A. So from looking at this, you can see that VA here and VA here cancel out. So this is equal to VR minus V infinity, which is equal exactly to what we were working with earlier. Okay, this is VR minus V infinity, or potential at R with respect to infinity, which is exactly the same as what we were working with our simpler case, potential outside. The reason we had to split it up mainly into this more complicated expression is because the electric field differs whether you're inside or outside the sphere. But if you rewrite these integrals in terms of this formula that we know, then it becomes a little more intuitive mathematically, at least. Once you work out all the algebra here, oh yeah, you can also for this term right here, yeah, you'll notice it's the same integral basically as this guy, which we already did, except we integrate to A. So you can take this and just let R equal A. Okay, and you're going to end up, after doing some algebra, with rho times A squared over 3 epsilon naught minus, after doing some more algebra, rho naught over 6 epsilon naught times R squared minus A squared, which can be further simplified to rho naught over 6 epsilon naught 3A squared minus R squared. Okay. And finally, for this first method that we just worked with, your potential can then be expressed as rho naught over 6 epsilon naught 3A squared minus R squared when inside the sphere, and rho naught A cubed over 3 epsilon naught R when outside the sphere. Okay, so the second method, it involves indefinite integrals. And this is the method, one of the methods that the textbook uses. Um, so again, when you integrate something that's using an indefinite integral, you would get a constant of integration at the end. Okay, so the way that fits into the whole potential situation, you'll see in a second. So again, just like the first method, you're going to want to start by finding potential outside the sphere. So again, that's case 1, where every time r appears here, we're going to assume it means that it's greater than a already. And now we're going to use the same line integral equation like this, but we're going to not specify any bounds here. We're going to put the same electric field outside, which is rho naught a cubed over 3 epsilon naught r squared dr. And when we integrate, we're going to get the same thing, except we're going to get this guy here. Let's call it C1. We're going to get this constant now because we use an indefinite integral. This is one of the ways that the textbook deals with these sorts of problems involving potential. So the idea here is this constant is supposed to represent the potential at some reference point. Okay, and typically, unless assumed otherwise, you can assume this reference point to be infinity, and the potential at infinity is typically assumed to be 0, at least for like all the problems I've seen and all the situations I've seen in this course so far. Unless otherwise specified, you can take potential at r goes to infinity as 0. So since we're talking about the potential outside the sphere, any r outside here, again, because we're going from the outside to inside, any r here is going to be with reference to infinity. So that means the C1 is referenced to infinity, which means that the C1 we can write as just 0, basically. And now for the second case, you'll also notice that our answer for the first case is actually exactly the same as how we got it for method 2. Now, this is where you'll see the major difference. To find the potential inside, we're going to use just one integral for now, an indefinite integral, and we're going to plug in the electric field inside the sphere there. Okay, and then when you integrate that, you're going to get rho r squared over 6 epsilon naught plus C2. So once you get here, you're going to see that you have this other constant of integration. But we can't just as easily say this is with reference to infinity and that this is going to be 0, because we're now talking about inside the sphere and there's this other non-zero potential around it that we need to talk about. So long story short, you can't just say the C2 is anything. We have to solve for it. So to do that, I usually find that it helps, and the textbook does this too, to piecewise define potential like this. It's equal to our rho naught a cubed over 3 epsilon naught r when we are outside the sphere, and it's equal instead to negative rho naught r squared over 6 epsilon naught plus our mystery C2 when we are inside the sphere. So what you need to do now is you need to basically equate these two right at the surface of the sphere where r equals a. So when r equals a, you can equate these two potentials basically. I won't go over the specifics because I don't know the specifics or how exactly it works out. In some questions, they define these boundaries as strictly greater than or strictly less than, and in some, I see them being defined as like this, greater than or equal to, or less than or equal to. But I'm not going to talk about that stuff because I don't know exactly what it is, whether it's strictly greater than or equal or whatever. But basically, when you equate these two and you let r equal a, you get this. And now, look at that. You can solve for C2 in terms of all this stuff. Okay. And once you do, you'll be able to plug in C2 for what you find here. And then once you do that, you're going to find that this thing is going to equal the exact same result as what we found earlier, which was this, when r is less than a. So to recap, with this indefinite integral method, it's fine. It might work a little better for you if you're not so comfortable doing the other method with the definite integrals and you're not sure why the bounds are what they are. But here you need to know that the constant, where is it? Oh, I deleted it, that's why. So you need to know that the constant of integration here is 0 when you're talking about reference to infinity, but otherwise you can't say what it is just yet. You need to piecewise define your potential and equate the two at the surface of the sphere, otherwise known as when r equals a. Let every r in your potential equal to a. Plug it in, equate them, and solve for C2 in terms of the same things. And then plug your C2 back into here, and you should get the same answer as you did with the definite integral method.